Hello, everyone. Thank you for joining us. My name is Mahmoud Raoufi. I'm a professional engineer, professional traffic operations engineer, and a PTV certified trainer since 2015 for Visum, Visim, Bistro, and Biswak. I have been modeling traffic since 2008, and I have been focused on large-scale microsimulation, detailed regional models, dynamic traffic assignment, and dynamic matrix estimation. Today, I'm going to talk about the accessibility analysis. I first start with the definition of the accessibility and the methods of presenting the accessibility, and then I will talk about the model preparation and setting up the assignment. So what's the accessibility? If I want to start with an example, the accessibility is the number of jobs that I can reach to from my home within a reasonable amount of time. In a more technical way, the accessibility is the number of attraction units like jobs, university seats, hospital beds, any type of attraction unit. The accessibility is the number of attraction units reachable from a zone while accounting for the desirability of travel, which is called travel acceptance. In this equation, which is color-coded based on the image, we can see that the accessibility of origin is calculated as the summation of utility of travel from the origin to each destination multiplied by the number of attraction units at each destination. When we talk about the accessibility, we mainly refer to the accessibility via transit. That's because transit is a low-cost means of travel available to all members of the community. Not all members of the community can drive or have access to a car. Some of them are too young, too old, or they cannot afford a car. Using transit, we provide them growth opportunity equal to the rest of the community. So we are promoting equity through transit. Moreover, we try to encourage private transport users to change to public transport. That's because this way we can save budget on transportation infrastructure, and also transit makes less emission. And so as a result, indirectly, we are again promoting the equity. Let's focus on the equation. So in this equation, as I mentioned, we are showing travel acceptance as utility of travel from origin to destination. This utility can have different forms. It can be simply inverse of travel time or the inverse of exponential function of travel time, like in here. It can also have other forms depending on what works best for our analysis. In this graph, we can see how the utility function changes our results, or basically how it works. If we consider the orange line with the beta factor of 0.015 to interpret the results, we can see with a trip of 15 minutes, 80% of the people will accept this trip as desirable. Or in other words, for an individual, there is a chance of 80% that the individual accepts the trip. When it comes to travel time of 60 minutes, then this percentage drops to 40%. And if we want to consider the impact of selecting beta, which is the sensitivity factor of this model, we can consider the blue line here or the green line. The blue line is the least sensitive model with the value of beta equal to 0.01. And if we consider the travel time increases from 0 to 60 minutes, then we can see that 45% of the people react to this change. They don't want the trip anymore. While with the most sensitive function, this percentage drops by 70%. Only 30% of the people will still accept the trip as desirable. So this shows the impact of the calibration factor beta. In addition, the impedance function in here does not necessarily need to be limited to travel time. It can include distance, cost, and discomfort, like when the vehicles or stations stops are too crowded or feel unsafe. If we have data on these parameters, and if we can calculate their weight factors relative to the main parameter, which in this case is travel time, then we can include them in the impedance function. How to choose the form of utility for these parameters depends on, in my perspective, other studies, because in here we don't have any parameter or measure to calibrate the function based on that. We have to use other studies, other models in the region, for example, or in similar cities to come up with the factors, to come up with the form of function. Or we can perform a stated preferences survey to calculate these values. Or we can analyze the data available to come up with the distribution of travel time in our network, so that we can select the form and calculate the parameters. So before I explain how we can present the results of accessibility, I have to mention that for this study, I have studied Greater Austin area. I have used Census Bureau data of jobs and population in each census block group, and the GTFS file of Cap Metro, that is the transit service provider of Austin area. So in this image, which is the first method of presenting the accessibility, which is what we already discussed, each zone is colored based on its accessibility value, which is basically number of jobs available, reachable from that zone within a reasonable amount of time. So the attraction units are the number of jobs, and the utility function is the inverse of exponential function of perceived journey time. And the beta factor was selected as 0.015. This method is exactly implemented in Visum, and here is the dialog for that. First, on top, we select the layer of data that contains our attraction potential or attraction units. And then we select the parameter itself that contains the data. Next step will be to select the impedance matrix, which in this case was perceived journey time. And then we can type in the beta factor. And then at the end, we select how we want to save the results. As I mentioned before, accessibility is calculated for each zone as just a scalar value. So we can just select an attribute of the zones to save the results. Or if we want more details, we can determine a matrix or define a matrix to keep the results. And the arrays of the matrix will be utility of travel from I to J multiplied by the potential attraction units of the destination. This way we can use the results for further analysis to calculate weaknesses and strength points of the accessibility of each zone. But while this method has advantages like it's easy to present with an image graphically, and its utility function and also the results are continuous and so are more accurate, it has an issue because the unit of the results is, like in this case, jobs by some form of time, which is not tangible. So to overcome this problem, we can additionally present the accessibility with a different method. In this method, we first define classes of travel time, like up to 15 minutes, 30, 45, 60, and beyond 60. And then for each origin zone, we classify the destination zones into each of these categories based on their travel time from the origin to that destination. So as the result for each origin zone at the end, we have a graph like this, which presents the number of trips, the number of jobs available within 15 minutes, 30, 45, and 60. Also, it is easier in this case to present the results in a tabular form. Presentation of the results graphically in this case is not that easy because of overlapping issue when we zoom in and zoom out. And also if we include, for example, in this case, the jobs available beyond 60 minutes, then it impacts the visualization of the other groups. So the two methods together can support each other and support our presentation. Just to provide an overview of two other analysis of transit supply and compare them with the accessibility analysis, I have included two slides in here. First analysis is isochronous analysis. In the isochronous analysis, we select one zone and calculate the travel time from that zone to any other location in the network, and then display the network based on the travel time, color the network based on the travel time. It can also be the other way. It can be towards that zone. And so the isochronous analysis is only about travel time, about the trip itself. It doesn't take into account the land uses that we have in the origin or destination. The other analysis that we can do is catchment area analysis or service area analysis, which is actually the area that each stop or station covers in our network. So if we intersect or overlap this layer with our land use data, we can determine how many people or how many jobs we are providing service to. But in this case, we don't study anything about the travel time. In the accessibility analysis, we somehow combine these two methods of analysis. But I don't mean that we just can use the accessibility analysis. I mean the accessibility considers these two parameters together, and each of these methods have their own use cases. So let's talk about model preparation. As I mentioned before, I use Census Bureau data for the population and employment number in each census block groups. Employment in each census block group is not directly available, but eventually the source is Census Bureau, and with some processing of data, we can prepare this data. Next step will be the import of GTFS file, and we can import the GTFS into Visum, which opens a new or a blank Visum file and imports the data into that file. And usually, most of the time, default parameters of this dialog should work fine. We need to just take care of the calendar period. We have to make sure that it is set to the proper value. And here is the result of the import. And I can explain about these transit objects of Visum later. Next step is public transit supply import. This step is specific for the condition if we have multiple operators in our region and each of them has its own GTFS file. So when we import the GTFS files, they are imported into separate Visum files. And then at the end, we need to combine them together in just one file in order to be able to perform the analysis. Another use case of this dialog is to project our public transport network on our street network. So in either of these cases, we can use this dialog, import of public transport supply. And this is not a one-step process like the previous one. This should be broken down into as many steps as possible, and it is an iterative process, and so we need to keep track of every single step, and also through defining user-defined attributes, we have to keep track of every single change that we make to the network, or better to say Visum makes to the network in each running of the process. This way we can find the errors, go back into the process and resolve the issue, and again rerun, reiterate the import. So after this step, we need to simplify our network, because as the result of all those changes and the imports, there are now items in our network, objects in our network that are actually supposed to be just one, but they are now copies. There are now copies of them in our network. So with this dialog, we can just combine them together, and the dialog works based on the proximity of the objects, and also we can optionally select it to work based on similarity in the names. So after this simplification, then we need to bring in the walk network. So the best way to do that is to download the walk links or walk network from the OpenStreetMap and then merge it with our network. We need walk links in order to more realistically model the transfers between different stops, where the passenger needs to come out of one stop to the network and walk, and then enters the other stop and takes the other line. Transfers within the stops can be handled through edit stop dialog. Next step will be connecting our network to the zones. In here, we had around 1,800 zones, and the zones were census block groups of year 2022. And there are two methods of creating public transport connectors. One of them is the original version, which is implemented in Visum, and the other one is an add-in, and each of them has its own advantages. So we can use both of them to create the connectors. And then final step will be to set up the timetable-based assignment for this purpose. There is no actual assignment in here. It's actually just calculating the scheme matrix, because we don't have any demand, but the dialog is the same. So in here, the assignment period or the scheme calculation period starts from 6 a.m. to 8 a.m. with a post-assignment period or extension period of 1 hour. And the impedance function was actually like this. In here, to come up with the perceived journey time, we multiply all walk times by 3 in order to account for the difficulty of walking. And additionally, we add a 10-minute penalty for each transfer, which is different from transfer wait time. It's just a penalty to account for the difficulty of transfer. And at the end, we can run the process and come up with the results and present the results with the two methods that I mentioned before. Thank you. And here is my contact information. It's actually the link to my LinkedIn profile. If you have any questions, I'll be happy to answer.